Okay, here we have a Calculus 1 example on continuity. So we have a graph here with a function in red. There's a little dot down here at the point 0, -4. And we have a question saying, is f of x continuous at x equals 0? So we can see f of x is basically the part in red. So we have what looks to be y equals x squared in this curve in the top half of the graph. But then we do have one point in red down at the point 0, -4. So we want to know, is it continuous? So what does continuous really mean? Well, the easiest way to describe it is, can you draw through the point where x equals 0 without lifting your pen? And clearly, I'll try and do it in orange here. As we draw along the line, we can't go through this point where x equals 0 without coming down here and drawing it in here. So I had to lift my pen to do that, and then I'd have to lift it again to continue the rest. So I can't go from the left of x equals 0 to the right of x equals 0 without lifting my pen, so I know that this is not going to be continuous. So that's the easiest way to sort of think about it, but how do we go about actually proving this algebraically? So there's one quick rule to know if a function is continuous at a point. Let's say that point is x equals a. In this case it's 0, but we'll just call it a in general. It is continuous if the limit as x approaches a of f of x exists and it equals f of a. So what this means is, the left side we have to say that this limit actually exists. Now most of the time you'll have to test from the left and from the right, and those have to be the same in order for the limit to exist. And then the right side of the equation is really saying, okay, is the function defined at the actual point? Because remember, we can have a limit exist as we approach that point, but then does the function actually exist at that point, and are those two values the same? So first of all, let's look at the limit as x approaches, remember a is 0 here, so as x approaches 0, of f of x. So we can see as we approach this point in the middle, is the y-axis is where x equals 0. X equals 0 on this y-axis here. So as we approach from the left, we're following this path, this path, this path, and it's getting very, very close to y equals 0 as x approaches 0. What about from the right? Well, we're following this path from the right. This is how the function's going. It's getting closer and closer to 0 as well. So this limit is approaching 0. Remember, the limit is as the x value gets very, very close to 0, what is the y value getting very close to? And we can see the pattern. It's going very close to the point 0, 0. Even though it's not going to hit there, that's kind of where the pattern's going from both sides. So I would say the limit as x approaches 0 of f of x equals 0. Let's look at the right side. F of a, or f of 0, what does that equal? Well, this has nothing to do with the pattern where we're coming from, left or right. This is the actual y value of the function when x equals 0. So let's look at that. We can see this open hole here. That means that we get very, very close to that point without actually touching it. And the point on the function where x actually equals 0 is down here at the point 0, -4. So we would say, okay, when x equals 0, y equals -4. That's the same as saying f of 0 equals -4. Therefore, the limit as x approaches 0 of f of x is unequal to f of 0, because the left side's equal to 0, the right side's equal to -4. So the function f of x is not continuous at x equals 0. So again, we're always looking for two things. Sort of one, what does the limit as x approaches the value a, what is the y getting very, very close to? And then what is the actual value if you were to plug in x equals a for the function? What is the actual y value at that point? If those two are the same, then the function's continuous at that point. If they're different, the function's discontinuous.